Our first unit is going to be on momentum, and in this unit we're going to look at momentum in general, we're going to look at the conservation of momentum, and we're going to look at impulse. And so let's start off with momentum. So when we have a, oops, go on here. The momentum of an object is basically defined in physics as being the product of the object's mass and its velocity. And so, just using a very simple equation is that momentum, in this case, the symbol for momentum is P, is going to equal to m times v. And so P is the momentum. It is a vector because of the fact that mass is a scalar and then times velocity a vector. That'll give you a vector when you do that. So momentum is a vector, so it does have direction. And we would just do it by measuring that mass in kilograms times the velocity in meters per second. We get that, and that'll give us the momentum. The units of momentum are going to be in the sort of not very nice unit, a kilogram meters per second. That would be the unit of momentum here. Now, you may ask, why is momentum P? Well, the most obvious reason is because of the fact that the most logical symbol for momentum would be m, is already used for mass. There are some schools of thought that basically say that the reason why that momentum is p is it comes from a Latin word that basically means to go toward. It's actually the same root as the word centripetal, the P-E-T-A-L. But that hasn't really been proven historically. So for right now, you just have to buy the fact that momentum is going to be expressed by the letter P. So as we said, P is the momentum in kilogram meters per second, m is the mass in kilograms, and v is the velocity. So you just take the product, that gives you the momentum right here. And so as we said, note that P and V are both vector quantities, both the momentum and the velocity. And so for this to be true, the direction of the momentum must always be the same as the velocity vector. And so if we have some object that's traveling at, say, 3 meters per second in this direction, and let's say that object has a mass of 1 kilogram right here, to find the momentum, we would say, okay, the momentum is going to be the mass 1 times the velocity 3, and so we'd say our 1 kilogram times our 3 meters per second. We get a momentum of 3 kilogram meters per second in this same direction. And so that momentum that goes in there is in exactly the same direction as the velocity. Also note that if the velocity changes direction, the momentum must also change direction. So if we had an object that was traveling in a path like this, and so its velocity is changing because its direction is changing, even though the magnitude is not changing, it may be traveling the same speed the whole way around, the momentum would change along with it. And so that is something to keep in mind whenever you work out momentum problems like this. So once I get this all erased, we'll go on to our next bit here. So let's see. All right, so moving forward, conservation of momentum. And so this is probably the biggest thing that makes momentum a useful thing to work out in physics problems. And that's that if we have a group of objects that neither gains nor loses mass, so we're not adding mass, we're not taking mass away, and it's not acted on by an outside force, it's called a closed system. And so closed system means no mass is being added. It means that we're not having any outside forces here. Internal forces are okay. And so if we had, say, a box that had 2 people inside of it, and these 2 people were fighting each other, they're putting forces on each other. But because of the fact that this is a closed system, no people are coming inside the box, no forces are coming from the outside onto the box, is that we would say that this object right here would be a closed system, because while these little guys inside here do put forces on one another, they don't have any external forces from the outside that are acting on them, and we're not adding mass. So that's a closed system. A weird example of one, but it's still a closed system here. So for such a closed system, where you have the system neither gains mass nor loses mass, it isn't acted on by an outside force, the total momentum always remains the same. So this is called the law of conservation of momentum. That when you have a closed system, the total momentum before and the total momentum afterwards are the same. So if you have, imagine, 2 boxes which are traveling towards one another, they collide with one another and they stick to each other. If you were to find the momentum of the first box and the momentum of the second box and add those together, that the total momentum of these 2 boxes before the collision and the total momentum of basically the collided, boxes that have come together here, and you added those two momentums up afterwards, that the sum of each of those momenta combined would be equal. The total momentum before the collision and after the collision is the same, because in this situation, we did not add mass to the boxes before and after. We have no external forces. The forces between the boxes are all internal. And so as a result, we would basically say that the total momentum is the same. And this becomes really useful because if we knew, just, for example, the mass and velocity of this first box, we could find this momentum. And if we knew the mass and velocity of the second box, we could find the momentum. And then the question was, well, how fast is this conglomeration of two combined boxes going? Well, we could figure that out because once we know the two original momenta here, then we can use that to find the total momentum. We know the total momentum before and the total momentum after are the same. And so then we'd be able to say, hey, these two added up are going to equal to the total mass, and so the mass of the first box plus the mass of the second box, because they're combined now, times the velocity of those two boxes. Well, to find this momentum and this momentum, we had to know the first two, we had to know their masses, and so we can add those two masses up, multiply it by the velocity, and that should make this work out, and we can solve for that velocity here. So, as it sort of notes in the second part on the third bullet here, said it means in a collision between multiple objects that make up a closed system, the total momentum of all objects is the same before and after the collision. And so, as a result, we say they're conserved. So let's actually work this out with numbers. So at the bottom here, we have a red ball and a blue ball. We have a stationary blue ball. It's going to be hit by a red ball, which is moving at 4 meters per second. The red ball has a mass of 3 kilograms. The blue ball has a mass of 6 kilograms. And so what's going to happen is the red ball hits the blue ball, they collide sort of on our middle section here, and then afterwards what we're told is happening is that the blue ball is heading off at 3 meters per second right there, whereas the red ball has bounced backwards and is now heading back in the other direction. And so let's work this out and show that momentum's conserved, that this is consistent with reality here. So first let's figure out what is the momentum of our red ball before the collision. And so to find that momentum, we know the momentum of the red ball is going to be equal to its mass times velocity. The mass of the red ball is 3 kilograms. That's a 3 right there. Okay, that is kilograms. Times the velocity of the red ball, which is 4 meters per second. Okay, now in this case, the 4 meters per second is heading off to the right, so we are, for the purpose of this, going to call that the positive direction. So the original momentum of the red ball before is basically going to be equal to 3 times 4, so it's going to be 12 kilogram meters per second. I'll leave the unit off, but you know what it should be here. The blue ball before the collision, however, if we want to find the momentum of it, then we would basically go and say, all right, well, the momentum of that one is equal to its mass, which is 6 kilograms, times its velocity, which is 0. And so it would have a total momentum originally of 0. Okay, so that's the momentum of the blue ball. So if we were to actually combine these together, we would say, all right, let's look at total. So the total momentum before the collision. The red ball before the collision has a momentum of 12. The blue ball before the collision has a momentum of 0. So our total momentum before, and the total momentum is also going to be the total same after, is going to be 12 kilogram meters per second. All right, so this should be our check here because this is the total momentum before. That should also equal the total momentum afterwards. So let's find out the total momentum afterwards. Let's look at our red ball afterwards. So the momentum of the red ball afterwards would equal to its mass, which has not changed. It's still going to be 3 kilograms, times the velocity of the red ball. In this case, the red ball is going 2 meters per second, but to the left. And so it would have a velocity of -2. And so when we solve that, that means that the red ball after would have a momentum of -6 kilogram meters per second. Okay, now next thing to talk about is about our blue sphere. And so for that one right there, the momentum of that should be its mass, which is 6 kilograms, times its velocity, which is 3 meters per second. And so we'd say 6 times 3 is 18. The 3 is in the positive direction here. And so as a result, we would say the momentum of this one afterwards is going to be 18 kilogram meters per second. And so if we wanted to find the total momentum, then we'd simply add these up. We'd say the total momentum afterwards is going to be equal to -6 plus 18. We add those up, we get a total momentum of 12 kilogram meters per second. And, looking at what we've got here, total momentum of 12 kilogram meters per second afterwards. We got a total momentum of 12 kilogram meters per second before. And so as a result, we can see that momentum is conserved in this situation. This is basically a situation where that would be physically realistic. because of the fact that momentum is conserved. Now note that if we had needed to, if we did not know, say, how fast the red ball was going after the collision, if we didn't know that number, we could have solved for it. Because by figuring out what the original momentum is, and figuring out what the momentum of one of the two objects is afterwards, we could then subtract the momentum afterwards of one of the objects from the total, because that total is the same before and after. We get 12 regardless of which side we're on. And then once we've done that, we would know the momentum of the red ball. Once we know the momentum of the red ball right here, we could use that to solve for a velocity if we did not know what that was. And so that's an example of sort of how we might use some of these calculations for momentum to solve certain problems. All right, so let's go ahead. I'll get this guy erased here, and we'll go on to our next situation. And what we're going to look at there is this question of, so this situation we did here is in one dimension. These balls are only moving right to left. But what would happen if we had something where one of our objects or both of our objects end up moving at an angle? And so in an angle, we're going to have to still use the same rules, but it may look a little bit different. So if the collision is two-dimensional, the momentum is conserved in both the x and the y directions. So in this case, at the bottom, we have a red ball that's going 4 meters per second to the right, a blue ball that starts off going 0 meters per second. So they collide. But because they're offset slightly, is that what ends up happening is we end up having the red ball moving at a 30-degree angle from this, so it's 30 degrees in that angle right in there, at 2 meters per second. And the blue ball is going to be traveling with an angle right here of 60 degrees, so that's a 60-degree angle right in there, at 1.73 meters per second. And so let's verify that, at least within the significant figures, is that the momentum is conserved. So what we're going to do here is we're going to say, hey, let's find the original momentum in both the x and the y directions, and then let's find the final momentum in both the x and the y direction and verify that they're the same. So let's look at, say, our red sphere before. And so we'll look at the red before, and we're going to look at x, and we're going to look at y. Okay? And so for this one, in the x direction, the red sphere has a momentum that should be equal to mass times velocity. And so the mass of the red sphere is 3 kilograms still. I have not changed that. The velocity is 4 meters per second. And so that means that the momentum in the x direction for just the red sphere at the beginning is going to equal to 12 kilogram meters per second. All right. In the y direction, the red sphere has 0 momentum, for the simple reason that it's not moving up or down. It has no velocity in the up or down direction. It's only moving in the positive x direction. We'll still call that direction as being positive to the right. And so since it has no momentum in that direction, its total momentum is 0 originally in that y direction. Next thing we want to look at is, let's look at the blue sphere before the collision. Same thing. So the momentum of the blue sphere before the collision, we would say its mass times its velocity. Well, its velocity is 0. Therefore, we can say that its momentum in the x direction to start with is 0. In the y direction, the momentum is also 0 because it's not moving anywhere. And that should be an equal sign, not a less than sign. All right. So we can figure that out. So we've got the red and the blue. And so if we were to look for the total momentum in the x and the y direction, and so now we're going to look at total, that we would say the total momentum in the x direction before, so px right here, total, would be equal to 12 plus 0. And so we get a total of 12. The total momentum in the y direction to start with should be the sum of the two. 0 plus 0 is just 0. So we have a total momentum of 12 kilogram meters per second in the x direction. That should be the same after the collision. And we have a total momentum of 0 kilogram meters per second in the y direction, which should be afterwards. Now afterwards here, it's going to be a little more difficult because of the fact that now we have balls that are going off at angles. So what we want to do is we first want to say, hey, I can either figure out what is the component of the velocity in the x direction and in the y direction for each, or what I could do is I could go and say, I'm going to figure out the total momentum originally and then break that into components. You'll get the same result regardless. It really doesn't make a difference which one you want to do. In this case, I'm going to go ahead and I'm going to set this up and try to solve for the x and y components of the velocity for our two afterwards. So let's start off by setting up a velocity triangle for our red sphere. So the red sphere is going in this direction has a total velocity of 2 meters per second. But I'm going to break this up into a Vx and a Vy. And so since we know this angle inside here is 30 degrees right in there, then we can say, all right, so the side that's on here should be 2 cosine of 30. I don't know if you can read that. The one up here should be 2 sine of 30. Okay, now we can solve that out. So let's see, which is actually one that you should be able to do in your head, because the sine of 30 is just 1/2. And so this would just be equal to 1. Whoops, might help if I actually had a pen out. So this would just be equal to 1 kilogram meter per second in the x direction, and then 2 cosine of 30 is going to be 1.73. And so that means that we get a value of 1.73, that's a 7.3 right there, is going to be the component that's in the y direction. So let's see if we can get this to work off with the blue sphere. For the blue sphere, once again, this one's traveling sort of in a downward direction, has a magnitude of 1.73 as its velocity. We have two vectors, we have an x component and a y component, we have a 60-degree angle in between them, and so then our adjacent is going to be 1.73 times the cosine of 60 right there. And so if we do 1.73 times cosine of 60, we get 0.866025, 0.866025 right there is going to be our component. Technically it's going to be negative because it's going downward. In the y direction. For our x direction, this should be 1.73 sine of 60. And so 1.73 times sine of 60 would equal to 1.5 is what I get. Let me double check on that, see if that's reasonable here. So 1.73 times 60 sine, yes, 1.5. And so 1.5 meters per second will be our velocity in the x direction. So now that we've got that, let's set up the same type of problem that we did before here. What we're going to look at is we looked at our red before and our blue before. Now let's look at our red after the collision, still in x and y. So the momentum in the x direction for the red. Well, the red starts off by going what velocity? Well, as we said before, we figured out it's going 1 is its x component. So it has a velocity of 1 times its mass. The mass of the red sphere is 3 kilograms. And so that means that our final momentum in the x direction is going to be equal to 3 kilogram meters per second. All right, our next one will be in the y direction. So in the y direction is that Py should be equal to, once again, the mass times the velocity. And so the mass is going to be 3. The velocity in the y direction we found was the 1.73. And so we say 1.73 right here. And so that gives us a y momentum for the red afterwards of the 1.73 times 3. And so 5.196 is what I get. 5.196 kilogram meters per second. All right, so we have an x component of the red ball's momentum of 3, a y component of 5.196. And so then we can go ahead and say we've got red. Next, let's look at blue. And so let's look at the blue after the collision. And so after the collision, we look at the momentum in the x direction should be equal to the blue's mass. The blue's mass is 6 kilograms times the blue's velocity. The blue's velocity in the x direction we found to be 1.5. And it is positive. It's still going off in that direction here. So we say 6 times 1.5, and so we get a total of 9 kilogram meters per second in the x direction. And then in the y direction, we'd say Py should be equal to the mass, which is 6, times the velocity. And the velocity in the y direction is negative 0.866025. Negative 0.8668025. And so we say that right there. All right, so give me a second, put that in. So the 0.866025 times 6 gives us 5.19, negative 5.196 kilogram meters per second. All right, last step. let's find our total momentum before and total momentum after. So for our total momentum after, so for x and for y. So for the x direction, we got a total momentum, we got a momentum of the red sphere of 3 in the x direction and the blue sphere of 9. The sum of those two means that the total momentum in the x direction afterwards is equal to 12 kilogram meters per second. And we started off at the very beginning getting a total of how many? 12 kilogram meters per second. So we get the same value before and after for the x direction. We should have the same thing happen for y. So taking a look in the y direction, we would say, all right, total momentum for y should be the sum of the two we had. So in the red ball had a y momentum of 5.196. The blue ball had a total momentum of negative 5.196. The total momentum in the y direction is 0. And so the original total momentum in the y direction is 0. Final total momentum in the y direction is 0. And so you can see that momentum is conserved both in the x and in the y direction for a physical case like the one that we have right here. Like the last one, if we needed to solve for something, we could have used this to solve by working this sort of backwards. If we knew what the original momentum of this was, right, of these two right here, then we can use that to find the original x and the original y momenta of either one. And then once we have those two, then you can use those to get these two momenta, the totals before and after. And if we knew, say, what this ball was doing, but not what that ball was doing, that was the one we don't know, then we could figure out information about that. Because once we knew the blue ball's position afterwards, we knew what its momentum in the y direction is, we could use that to find the y component that's right here, because we know that y component has to cancel out with the y component that's down here. Once we had that, if we say knew what the, then we could figure out the x, because the fact that we know the total x has got to be 12, and we know the x on this one is going to be 1.5 times 6, and so that would be the 9. And so once you know that, you could figure out that this is 3. And then once you know that 3 right there, you could say, okay, the 3 is the momentum divided by the mass is 3 gives us a velocity of 1. And so then you can use that to find what this angle was if we didn't know it. And so we could use a system like this in conservation of momentum, even in a two-dimensional case where it's a little more complex, to figure out exactly what the mass and the not the mass, but what the velocity is of one of the other objects in the case of a collision. So that's basically what we're going to do in the case of a problem that has 2 dimensions. And so the next thing we're going to look at is we're going to look at another concept that's related to momentum, which is called impulse. And so impulse, I'll go ahead and tell you because it's going to take me a while to get this erased right here. Impulse is basically equal to the change in the momentum of a single object. Now we said that for a group of objects, a closed system, the total momentum stays constant. But you know, in a collision, that's not true for any one object. Each object sees a change in momentum, and the reason why it sees a change in momentum is because there's been a force applied to it. Let's see. Actually, I realized that I'm going to go ahead and skip to that. I'll come back to that problem later on. All right, so when we talk about impulse, the impulse is the change in momentum of an object, and impulse is given by the letter J, and so it's capital J because I stands for something else we'll see in the next unit. So J is the impulse here. It has the same units as momentum, kilogram meters per second, and it's just equal to the change in momentum. So if you can find, you have an object that has a momentum of 5 kilogram meters per second before collision, afterwards it has a momentum of 3 kilogram meters per second, then you know its impulse was -2, or the impulse on the object was -2. And so then we can use that to sort of answer some questions we'll see later on. Now, an object's impulse allows us to relate the force that caused the change in momentum and the time the force was exerted over. Because once we found that change in momentum and we know the impulse is also equal to the force times the time. And so in this case, this is the force that caused the change in momentum. And so if you have 2 balls colliding, then it's the force that the second ball put back on the first. And the time is the length of time that that impact caused, or the length of time that impact existed. And it doesn't necessarily have to be an impact. If we had, say, an apple falling from a tree, the apple starts off still up in the tree, so it starts off with 0 momentum. It falls, and as it falls, it speeds up, and so it picks up velocity and gains momentum. And so if we wanted to figure out, you know, hey, how long did it take to fall? One way to do it would be to say, hey, if I can find what that change in momentum is, then I can figure out the impulse. And if I know the force due to the gravity that pulled it down, then I can use the fact that I know that the impulse equals force times time to solve for the time. And so that's a little quicker than maybe using some of the kinematics equations, and maybe even a little bit quicker than using some of the energy equations to solve certain problems for time or solve certain problems for force. Now, the thing is about this problem right here, this particular equation, is this does assume that the force is a constant force. Or alternately, you could do it if it's an average force, if the average over whatever time period this is in here. Both will work for this. Well, we're not going to have to work out problems this way, just so you know, especially for those of you who are more calculus apt, is that if your force is changing and you need to find basically the force over some time, is that this is basically the equation down here that gives you here that impulses equal the integration of force as a function of t dt. And so you basically just go from the original time t1 to the final time t2 in your force. And if you integrate between those two over your force function, that will give you the impulse as well. For this class, though, we're only going to be dealing with average forces and constant forces. And so the equation that we have here should be just fine. All right, so let's take a look at working out an example of an impulse problem. And then we'll go back and do one more momentum, the one that we skipped earlier here. All right, so a 20 kilogram box sliding at 14 meters per second slows to a stop in 24 seconds due to a constant frictional force. And the question is, what is the frictional force on the box? So in our setup here, we have a, let's see, a 20 kilogram box. So we have some box, 20 kilograms is the mass. Starts off traveling 14 meters per second, right there. And it slows to a stop in 24 seconds. So after a total of 24 seconds, 24 seconds has gone by on the clock, it is now stopped. And so at this point, so here's our box at some point in the future, has a velocity of 0 at the end here. And so the question is, what's the frictional force? Obviously, there'd be a force to slow it down. So using our impulse equation, what we can do is we can say, all right, what I know is that my impulse is going to be equal to my change in momentum. Well, my change in momentum is just going to be the original momentum of the box, or the final momentum of the box, minus the original momentum of the box. That would give me my change. So let's see if we can figure these things out. Well, the final momentum of the box is going to have to be 0, right? Because the fact it's not moving. Velocity is 0, and so therefore it must have a 0 momentum. Minus the original momentum. Original momentum is going to be mass times velocity. This box has a mass of 20 kilograms. It has a velocity of 14 meters per second. And so then to solve this, I'd say 20 times 14. And so working that out, 20 times 14 gives me 280. And so then I end up with an impulse to start with of negative 280 kilogram meters per second. Okay? And so that is going to be my impulse. Now, what I know is that impulse is also equal to the force times the time if I have a constant force. Well, in this case is that this frictional force shouldn't be changing. The frictional force depends only on the coefficient of friction and on the normal force in the box. Since it's a level plane here, the normal force should be remaining the same. The coefficient of friction is also unlikely to be changing in this case. And so, and it tells us right here it's a constant frictional force. So we know it's constant, so we can use this particular equation. So we'll say, all right, the impulse is negative 280 equals the force, which is what we don't know, times the time. And so the time it takes to slow to a stop is 24 seconds. So 24 seconds right here. And so with this, we should be able to just divide both sides by our 24 right there. And we end up, when we do that, with negative 280 divided by 24 gives negative 11.667 newtons is our force. Significant figure-wise, we had a 20 kilogram box to start with. That'll round it to 1 sig fig. And so our final frictional force here is going to be equal to negative 10 newtons. So that would be our force on our box here. So this is sort of an example how impulse can actually really give you some answers pretty quickly. Once again, we could have done this by solving for the acceleration. You know, we know it starts at 14, we know it ends at 24, we know the time, or no, ends at 0, we know the time is 24, finding the acceleration and then applying the acceleration to the mass and using F equals ma. That would have worked for this. But this is an alternate method. Sometimes this method is more efficient. Other times using F equals ma is more efficient. But it's just another tool that's in your toolbox. So that overall gets us through our main examples that we have here. I do want to go back and take a look at that earlier momentum problem. But at this point, we've covered all of our new material. So if you feel like that you're pretty strong on this, feel free to go on to start doing some practice on this. If you'd like to see another example, then just hold on. It'll be coming up in just a moment. So let me get this finished being erased. And let's head on back, see what that previous problem was here. All right. So in this problem, we have a 75 kilogram man and a 120 kilogram boat. They're coasting at 5 meters per second. The man leans out of the boat, lifts up a 20 kilogram log from the water that was drifting toward him at 1.2 meters per second. And the question is, what's the new speed of the boat? So to give our general setup, we have a boat, maybe a little rowboat. There's a man inside said rowboat, and there is a log that's out here. There's our log. And so what we know about this situation is that we know that the man is traveling at a speed, and his boat is traveling at 5.0 meters per second. That is our original velocity. That the log is traveling in the opposite direction. We'll say its velocity is going to be negative 1.2 meters per second. Okay? Now, mass-wise, what we can say is we know that the mass of the boat is 120 kilograms. The mass of the man is 75 kilograms. But since they are traveling together, they're one object, they're both going to 5.0, we can treat them as the same thing and say that instead we have a man boat which is 195 kilograms for its mass, whereas the log is just 20 kilograms. All right, so this is our overall setup. Let's see if we can go ahead and solve. So whenever he picks up the log, that's a type of collision. This is, assuming that there's no friction on the water, a case where we have a closed system. Because between the man, boat, and log, there's no mass being added. Now, there's mass being added to the man of the boat because he's picking up the log, but this is a case where we'd want to include the log in that closed system to make the problem solvable. So of the system of man, boat, and log, there's no mass that's being added. Of the system of man, boat, and log, there is no external force. It's just the log on the man and the man on the log, and those are internal forces. And so as a result, we can basically say that momentum should be conserved here. These are traveling only in the x direction. There is no up or down direction or left-right direction in this case, and so this is a one-dimensional problem. We don't have to worry about breaking this into components. So let's look at what happens here. So let's look at the boat before. We'll look at the log before, and then we'll look at, honestly, afterwards. They're traveling together. And so what we really can do is for our afterwards, we can basically separate this into a boat log after. We can sort of treat those both together because of the fact that they are traveling as one object at that point. And so we still know the total momentum before and total momentum after should be the same. So let's look at the boat. So for the boat, the original momentum should be the boat's mass, which is 195 kilograms, times the boat's velocity, which is 5 meters per second. All right? And so whenever we take that, we can multiply that out. So we'd say 5 times 195. And so originally the momentum of just the boat is going to be 975 kilogram meters per second. For the log has a mass of 20 kilograms and has a velocity of negative 1.2 meters per second. So we can say the negative 1.2 times the 20, and so we find out that the log has an original momentum of negative 24 kilogram meters per second. So the question now would be, what's our total? So the total momentum should be the sum of our two individual momenta, and so then we'd say 975 for total momentum, so this is P total, should equal to 975 minus 24. And so when we do that, we find the total momentum is equal to 951 kilogram meters per second. Since this is a closed system, that means the total momentum afterwards is also equal to 951 kilogram meters per second. Now afterwards, we have a boat and a log all in one thing. And so we really can treat these like one separate object. And so for this, we would say, all right, let's find the momentum of the boat and log and man all in one spot. And so the mass of all three of these objects would be the 195 of the boat and the man plus the 20 of the log, because he's picked up the log now, he's lifted it up, and so as a result, we now have 215 as our total mass. The velocity we don't know, however, is that we would expect that he's going to slow down a little bit. He picked up something heavy. He should slow down a little bit. The log put a force on him pushing backwards whenever he picked it up. And so then we don't know what that is. But we do know that this momentum that we have right here is the total momentum. There's no other object other than the three of these together that's in this. And so that means we can take this 951 and substitute that in for our momentum. And so we'd say 951 is our total momentum, equals 215 kilograms times the velocity. We should be able to divide both sides by 215. And we measure out that our velocity then is 951 divided by 215, gives a total of 4.423 meters per second. Now let's apply the common sense test. The boat started out going 5 meters per second, and so 5.0. And so whenever he picked up the log would have pushed on him backwards because the direction the log is going against him, and so he should slow down. Sure enough, he ends up going 4.4. Just a slight slowdown, which is reasonable whenever you pick up a log like this. And so significant figure-wise, we have a 75 that has 2 sig figs, a 120 with 2 sig figs, 5.0 that has 2. The log only has 20. So looking at what we've got here, this is a little more complex. So let's see, the 975 should have 2 sig figs, is rounded to the tens place. Let's see, the 24 has a 20 kilogram log, that should be rounded to one spot, and so that would be the tens place. And so that means our answer should be rounded to the tens place. So if that's not rounded to the tens place, this means this has 2 sig figs, and then the 215 would have also 2 sig figs. Our answer should have 2. So our answer should just end up being finally a velocity of 4.4 meters per second for our final answer.